So because the tree can be used in any node, I can now calculate zero coupon bonds at time zero for any length. I can therefore calculate zero coupon bonds from any node into the future using exactly the same procedure. So for example, of this point, if I look at number 3, what I calculated at time 3 is the price at time 1 of a 2-year zero. That's what it is. It's the price at time 1 of a 2-year zero. Or I guess I should call it 3. It's the price at time 1 for a security that matures at time 3. 1 is the price at time 2 for a security that matures at time 3 from the upstate, and so forth. So from this collection of calculations, we can, in fact, fill out our lattice with the price of any zero coupon bond any place we want. So here I'm repeating the connection with Cox-Ingersoll-Ross, where I say we can value a bond by considering each path of interest rates separately, and if we enumerate all those paths with the associated probabilities, we can use that Cox-Ingersoll-Ross type formula. And that's represented this way. Notice the H, again, the R's would typically be annualized interest rates, and so the E star, it represents exactly the same formula we've seen with the integral Cox-Ingersoll-Ross. It's exactly the same thing. But in a binomial lattice, you can actually identify all the possibilities of paths of interest rates, whereas if you're generating them stochastically using a process for R, there are theoretically an infinite number of paths because you're using normal variables to drive the dz term. In a binomial lattice, we've reduced that infinite collection of paths to a finite collection, although a big finite collection, and we can feasibly actually enumerate every path from a binomial lattice, or we can sample from paths, whereas in the Cox-Ingersoll-Ross model we have to sample if we're doing it numerically because we can't generate all paths. The volatility of bond prices is going to be different than the what we see in the behavior of a stock. Stock volatility tends to increase with time. We know zero coupon bond volatility cannot increase with time beyond a certain point, because at some point the reduction in the duration, or the delta, the reduction in the sensitivity to interest rate moves offsets the volatility of the interest rate moves, and the bond's price becomes less and less variable. And then ultimately, of course, it matures for 1. So it has a volatility of 0. So the point again is that in this expectation, we are doing the expected value of the zero price using different paths in the lattice, which is very different than pricing a zero with the risk-neutral average of interest rates. We saw this earlier. It's a result of Jensen's inequality. The mathematics I repeat here, that the price of a zero at time 0 is the risk-neutral expected value of sums of this type. Notice the H as a multiplier for R. Jensen says because e to the minus x is convex, the expected value of this function is greater than the function applied to the expected value. So if we use the notation R0t, which is what we saw earlier, to be the t-year zero rate, the t-year spot rate at time 0, it's going to be smaller than the risk-neutral average of those interest rates from the lattice. And we saw this with the Cox-Ingersoll analysis. It's the same formula, same interpretation, same reason. Jensen's inequality gives us this inequality that the risk-neutral average of interest rates will always be too big as an estimator for the appropriate spot price. We can use exactly the same methodology for pricing options of the black formula type as well as caps. The same lattice is enormously flexible in terms of what we can do with it. Because remember, in Black's formula, we're looking for a call option or a put option on a forward 0. Well, if we have a binomial lattice, and let's say that we have a 3-year call option on a 2-year 0. At the end of 3 years in our lattice, we can observe what all the prices are of 2-year zeros at that time. In each one of the states at time 3 years, we will have the price of a 2-year 0, which we can calculate using the methods we've seen. Well, if we know the price of a 2-year 0 in each state on that lattice, we know the value of the call option. And once we get that, we do backward substitution using the spot rates in the lattice, and we now get the price of this call option that Black priced with his Black-Scholes type formula. Similarly with a cap. If I have a caplet, let's say I have a caplet which in time 3 provides a payment of the excess of the 1-year spot rate over 3%. Well, again, at the end of time 3 on my lattice, I can look at the 1-year spot rates. Any of those that are over 3%, I can determine the payment. I now have a series of payments at time 3 years that look just like call option values from the stock analysis, and I bring those back using the backward substitution calculation.